Hello, this is Rat Delane, and I'm going to show you how to make a quick example program in Glowscript showing projectile motion. Okay, so the first thing is Glowscript, glowscript.org. If you go there, everything's built in. As long as you have WebGL, then it should run your browser. But Glowscript is like JavaScript, and no lanky JavaScript. Okay, so I'm going to change this to CoffeeScript. So that's the first thing you want to do. Go up here and just add in CoffeeScript. And see, you get this warning. It says, oh, okay, you can use CoffeeScript, but you got to reload. So I reload the page. Okay, now I'm going to go kind of fast because you can rewatch this or play it in slow motion or whatever. So if you're familiar with VPython, it's very similar to that. Okay, so let me just start by making an object that I'm going to throw. It's a ball. So I'm just going to say ball equals sphere. Okay, now just like in VPython, you have to give it a position and a size at the we don't have to, but I want to do that. And the syntax is a little bit different. So the position is just going to be like this. I'm going to put it at the origin. Okay, so this says the position is a vector, and its x, y, and z components are 0, 0, 0. Now the size is a little bit different. I can say size. It's also a vector, which is maybe a little bit strange. And I'm going to give it 0.5, 0.5, 0.5. This says that the radius in the 3 dimensions is half a meter. Maybe that's a little big, but it doesn't really matter. You can change that later. You can actually make these different, and it won't be a sphere. It'll be, a spheroid, I guess that would be called. Okay, so that's wherever I always like to start right there and go ahead and run the program and see if it's working. So if I just click run, I ask you to save it. I did save it already. And you can see here that it makes a sphere. I can rotate it around. I can zoom in and out. Okay, so it's a 3D object that you can interact with. So that's good. Okay, so the next thing I want to do is I want to throw the ball. Okay, so I want to have some initial velocity. But I need to define some other things too. So let's just start off with the initial velocity as 2.5 meters per second. And I want to throw it at an angle theta of, let's say, 33 degrees. If I want to add a comment in here, you'd say meters per second, because that's what it is, and degrees. Okay. Okay, so with that, I'm going to determine, I need the momentum of the ball to start with. So I need the mass of the ball. I'm going to say ball.m as the mass, just so I can keep track of it easier. And let's say it's 100 grams, so 0.1 kilograms. Now for the momentum, I'm going to use the momentum principle here. So ball.p equals, okay, it's a vector. Well, it's going to be the mass of the ball, ball.m, times the vector. And the x component of this velocity is going to be 2.5 cosine 33. So I'm going to write that as v0 times cosine theta times pi divided by 180. So the cosine function built in here uses radians. So I converted this theta in degrees to radians right in there. And then I'm going to say the y velocity is v0 times sine theta times pi divided by 180. And then the z component is 0. Okay, let's just stop there and let's print. Print the momentum. Okay, and I'm going to run it. You can see right down there, it printed out the momentum. So I have 0.2 meters per second. No, that's kilogram meter per second. And 0.136. Let's just change something and see if it does work. Let's shoot it at a 45 degree angle. Then both of those components should be the same. Okay, so that suggests that it's working. Okay, so now I can get rid of the print. Doing things like that where you take a second to run a part of the program to make sure it's working is always a good idea. Otherwise, you can get finished with everything and have a mistake and have to redo a lot of stuff that you didn't even know was or was not working. So you have to be careful. Okay, so I need other initial things to start with. I need the gravitational constant. So the gravitational field G is going to be a vector. It's going to be 0, negative 9.80, okay, newtons per kilogram. I'm going to need the time, t equals 0, and then the time step. Let's just put this at 0.01. Okay. Now I'm ready to do my calculations. So let's just run this for half a second, and then we can change it. So I'll say while t less than 0.5. You don't have to put a colon there. I'm not sure why. In Python, you'd put a colon there. I don't really know what's going on. Okay, but you do have to tell the program how fast to run. You don't want the computer to go as fast as it can, or it won't look realistic. So I'm going to say rate 100 wait. So this says wait, do 100 calculations every second. And up here you see I have a time step of 1/100th. So this will make it in real time. Now what do I do in the loop? The same thing we always do. First thing is calculate the force. So the force, only force on the object is the gravitational force. So that's going to be equal to the mass, ball.m, times g. Now that doesn't actually ever change in this calculation, so I could do this just once up here. But I think it's a good idea to put it in the loop. So when you do things later, you can do it the same way. Next is to find the new momentum. So the new momentum is the old momentum plus F times delta t. So I can write that as ball.p equals ball.p plus F times dt. So here, remember, this is the equal sign. It means make that equal. It's not the algebraic equal sign. So don't get those confused. And also the order of these calculations does matter. Okay. Then finally, I want to find the new position of the ball. The vector position of the ball is ball.pos. That's R. So I'm going to use the position update formula. Ball.pos equals ball.pos plus the velocity, which is the momentum divided by the mass, ball.p times dt divided by ball.m. Now you may say, well, that shouldn't you just use the velocity and the acceleration? True, you could do that. But I think this is a better way to do it in the long term. Next, I'm going to update the time. And that's it. Let's run this program and see what happens. Okay, so it looks a little strange. But anyway, it looks like it might also be working. I think I must have. 0.5. Why is my... Okay, so one of the things that's happening is when I run this, it looks weird because the program is zooming out and zooming in to make sure that it takes up as much space as possible. So let's change that so that it doesn't zoom. And I'm going to make this ball a little bit smaller too. It's too big. Let's make this 0.1. And so if I go up here and I add the following, scene is a built-in property of the scene, and autoscale is scene is a built-in thing, and autoscale is a property of that. And if I set that equal to false, it won't autoscale. Watch it now. Okay, there's my little ball. See, it's zoomed way out, so that's maybe not so helpful, but at least it's a little bit easier to see. Let's just bump up the speed and make this a little bit bigger, just so you can see it. And run it again. There. That makes me happy. That's just for half a second. I could run it for longer if I wanted to. So let's in fact run this until the ball gets back to where it was. So I'm going to say while the ball position in the y direction is greater than or equal to 0. So now it starts off at 0, and it's going to run until it gets to 0. And then I'm going to do something else. Now I de-dented. Everything indented is in the loop. Anything not indented ends the loop. So I'm going to print out the final position. The final, let's print out the whole position, ball.pos. I'm going to print out the time. And so I can run this. And then there's my, it went 2.03 meters in the x direction. It ended at 0, and it took 0.64 seconds. So that's a thing that you could actually check. You could check that algebraically. You could do this problem. And you could add in a ground and all that other stuff too, but let's make it a little bit better. A little bit better, let me make a trail. There's a built-in function called attach trail. And if I put in the object ball and run it, see, it gave a little trail right there. Isn't that awesome? Okay, one other thing. I want to make a graph. So let me add in here a graph too. I'll call it graph 1, and it's a type of thing called a series. And you could give a color if you want, but I don't really care. And then down here, before I update the, well, I can put it right here. It doesn't really matter. I'm going to add a point to my graph. So I can say graph1.plot. Now I give it the x coordinate and the y coordinate of what I want. So let's plot time and ball.pos.y. Boom, there's a graph right there. See? That's exactly what you'd expect. Let's do one more graph. Let's plot the y position as a function of time. X. Straight line. That's what you'd expect, no acceleration. Okay, I can't help it. One more. Let's plot the y velocity as a function of time. So ball.p.y divided by ball.m is the y velocity. So it starts off with a positive velocity, it slows down and goes to negative velocity. Okay, that's it. You can I'll put the link to this program in the comment section, in the description. You can actually edit this program yourself. You can change things around. You can change the velocity, the angle. You can change whatever you want, and you can play with it. So that's your first Glowscript program. Congratulations. You'll probably have to watch this video more than once. Okay, bye.